This video is part 7 in a series about Super Nintendo Entertainment System features. This time, we'll learn how the processor communicates with external memories such as OAM, VRAM, and CGRAM. This will lead into Direct Memory Access, DMA, and eventually HDMA. Some of the devices the processor communicates with, in addition to main memory, are MMIO devices, which stands for Memory Mapped Input-Output. The amount of physical RAM in the Super NES is much less than the entire address space. As you will find out in a future video, some of these addresses in the address space are reserved for other things like controllers, cartridge ROM, and SRAM. However, there are memories that are not memory mapped and must be accessed indirectly. These include OAM, CGRAM, and VRAM. Instead, a memory-mapped hardware register is used as a pointer into one of these areas, and another couple registers are used to read to and write from the area at the memory location specified by the former. For example, to write something in the first location of CGRAM, first, the CGRAM address register at address 2121 must be set to 0, then the data to write should be written to 2122. Whenever a value is read from or written to these registers, the corresponding address register is incremented automatically, so data can be easily accessed sequentially. Here is a table that shows which registers are used for each memory. It is important to note that in these three locations, the data held at each address is 16 bits instead of 8 bits like in the main memory. In the case of video RAM, these 16 bits are spread out between two registers, but in OAM and CGRAM's case, the 16 bits are written 8 at a time in a single register. In addition to these three memories, work RAM can also be read or written to indirectly using its hardware registers. This might seem useless, but it allows direct memory access to work RAM, which results in a very speedy operation. If you haven't figured by now, these special hardware registers are used as part of the direct memory access process. Direct memory access is just a way to quickly move data from one place to another. More specifically, it allows transferring data between the A bus, aka CPU space, aka anywhere in the 24-bit address space, and the B bus, aka PPU space, aka any of the 256 registers of 2100 through 21FF. The reason why it is so fast is because it directly connects the data's source to its destination with no middleman, which would normally be the processor. Using the processor to load bytes from one place and store them to another is relatively slow, resulting in about 336 kilobytes per second. Even using quick pop slides, or even the move block instructions specifically meant for moving large blocks of memory, only give 358 and 413 kilobytes per second respectively. DMA, however, can reach speeds of up to 2.68 megabytes per second. This is incredibly useful when moving around huge amounts of data, like graphics. The SNES has 8 DMA channels, which means 8 transfers can be prepared at once and then initiated sequentially one after the other. Each channel has 12 dedicated registers, 7 of which need to be populated with the DMA properties that explain how the transfer will work. 3 registers are used to determine the 24-bit address on the A bus to transfer, while another register is used for the 8-bit address on the B bus. 2 registers are used to hold the number of bytes to transfer in total, and the final register holds all the other properties for the DMA setup. This includes which direction the data are transferred, whether or not to automatically increment or decrement the A bus address, and the format of one unit of data and how it should be sent over the B bus. As an example, here is how one would go about transferring a large block of graphics data from ROM to video RAM using DMA channel 0. First, the target VRAM address would be written to registers 2116 and 2117, and the B bus address should be set to the lower 8 bits of the VRAM data I/O register 2118. Second, the A bus address should be set to the location in ROM where the graphics data is stored, and the total number of bytes should be specified as well. Third, the transfer properties should be set. In this case, the transfer occurs from A bus to B bus. the A bus address should be incremented after each byte transferred, and the transferred bytes should be written 2 at a time in the order of low and high to match the VRAM data I/O registers. Finally, the DMA can be initiated by setting the channel's corresponding bit in the DMA enable register at 42OB. The least significant bit corresponds to channel 0, while the most significant bit is for channel 7. At this point, the processor would be suspended from executing instructions while the DMA transfer is occurring. Once the transfer is complete, it will be reactivated and execution continues normally. While generally DMA can be performed at any time, most of the registers accessible via the B-bus are used by the picture processing unit to display the image to the screen. Therefore, in order to read and write values to these registers, care needs to be taken so the PPU and CPU don't clash with each other while reading or writing data. Specifically, data should only be read or written by the CPU during certain blanking periods, one of H blank, V blank, and F blank. As shown in the previous video, enabling forced blanking in the middle of rendering can lead to a black streak across the screen, and trying to time this maneuver to occur exactly during H blank can be difficult. Luckily, there is an easy way to do this, and it is called H blank direct memory access, or HDMA for short. HDMA and DMA both use the same 8 transfer channels, so they can't use the same channel at the same time. They also use the same set of 12 registers, although for HDMA, only 5 need to be set manually beforehand, and 6 more are updated automatically during the transfer. One register holds the properties for the HDMA setup, and one holds the 8-bit address on the B-bus, just like the general-purpose DMA setup. The last 3 registers hold an address on the A-bus that points to what is called an HDMA table. All of this data only needs to be set once before initiating the HDMA by setting the channel's corresponding bit in the HDMA enable register at 42OC. After that, the data found in the HDMA table will be transferred to the specified hardware register automatically during H blank at the scan line specified in the table itself. The HDMA table is fairly straightforward and just includes instructions on what data should be transferred and when it should be transferred. It includes a list of data entries, followed by a single 0 byte which signals the end of the list. Each entry in the list includes a 7-bit line count, a 1-bit continue flag, and the data to transfer on that scan line. If the continue flag is clear, the data will include only a single unit, and it will be sent over the B-bus on this scan line. Then this channel will pause for the number of scan lines specified by the count before moving to the next list entry. If the continue flag is set, the data will include multiple units of data equal to that of the count. 1 unit will be sent on each scan line for this many scan lines, after which it will move on to the next list entry. Finally, if the count is 0, then this HDMA channel will be suspended for the rest of the frame. An additional setting in the HDMA properties register allows for an indirectly addressed HDMA table. This means that instead of the units of data being included in the table, pointers to the data can be used instead. This is useful for dynamic HDMA tables that are stored in work RAM. The pointers can be swapped out for others that point to different data tables in the ROM. As an example, let's look at how this windowing effect could be recreated using HDMA. To set up the HDMA transfer, we need to set the A-bus and B-bus addresses, as well as the transfer properties. Suppose the table is stored in ROM at address OBEOOF. Using DMA channel 3, that address will go into registers 4332 through 4334. The PPU register to modify in order to set the left side of window 1 is address 2126, so hex 26 will be stored into address 4331. Data is moving from the A-bus to the B-bus, so we reset bit 7 of address 4330. The HDMA table will use direct addressing format, not indirect format, so bit 6 stays reset also. And finally, the window register is write once and only 1 byte wide, so the transfer format is mode 0. This means each unit of data will only be 1 byte in size. Then, to initiate the HDMA transfer on channel 3, we set bit 3 of address 420C. This could be done by loading in the constant 8 into the register, but this would also disable any other HDMA transfers that were previously set up. Since the HDMA enable register is not readable, one way of properly initiating the transfer would be to set up all the channels first, then initiating them all at the same time. Another way would be to keep track of which channels are currently enabled in a separate register and logically OR with that value before writing it to 420C. Now, what would the HDMA table look like? The width of the left side of the window at the top of the screen is hex 60 pixels wide, and it stays at that position for hex 60 scanlines. So the first entry to the table would just be hex 6060. Set the register to 60, then wait for 60 scanlines. Then, for hex 10 scanlines, the position of the window changes every scanline. The line count for the next entry in the table would be hex 10, and the continue flag should be set. So the first byte would be hex 90 in this case. Then, hex 10 bytes should follow, which would be the position of the window for these next hex 10 scanlines. And finally, the position of the window doesn't change past this point of the screen, so the HDMA transfer is complete, and 0 should be written at the end of the table. HDMA is very powerful since it allows easy modification of many different PPU registers in the middle of rendering a frame. The end result of one frame of rendering is just that, a single image. However, the values of the registers used to create that image were not constant and changed over time. A great way of visualizing this change in the register is by recreating the image one scanline at a time by referencing a virtual copy of the screen that has the entire image rendered at once using only the values of the registers at that instant. The end result is something that looks very similar to the rolling shutter effect that occurs in real life with certain video cameras. Looking back at the windowing example, we see that even though there is only a single register that controls the left position of the window, it changes over time exactly when the image is rendered to produce the illusion that each scanline is controlled separately. The rest of this video will just be looking at examples of various PPU registers and what common effects can be produced by using DMA and HDMA transfers. By using DMA to write to OAM in the middle of a frame, the number of objects on screen can be artificially increased. This example was hinted to in the previous video. Super Mario Kart keeps track of 2 OAM mirrors, one for each half of the screen. F-blank is enabled in order to perform this transfer, which explains the thick black bar in the middle of the screen. If the animation is slowed down, each entry into OAM can be seen updating one after the other. Probably the most useful and versatile register to modify with HDMA is the background mode register. Many games will opt to render a HUD or text box in one mode and the rest of the game in a different mode. This allows for the main portion of the game to take advantage of the higher bit depth of one background mode, but allow the other portions of the screen to benefit from the multiple layers, like in Super Mario World here. Scrolling the background layers mid-frame allows for wave-like effects. In the first screen of Castlevania Dracula X, both vertical waves for the fire and horizontal waves for the background was used. By scrolling the background horizontally in large jumps, parallax scrolling can be achieved without putting each background element on a separate layer. In Donkey Kong Country 2, this effect is used for the clouds and the ocean combined. The most well-known usage of HDMA is to achieve perspective effects via Mode 7 scaling and rotation. Mode 7 transformations are strictly linear, so in order to have non-linear transformations, HDMA must be used to modify the matrix parameters every scanline. Many games made use of this effect, including F-Zero and Pilot Wings shown here. This was commonly used together with game mode switching in order to have a horizon and a background, as well as a HUD on a different background layer. The fixed color constant can be modified to create gradient effects with color math. It can be used to change just the back area color, such as this one in Yoshi's Island, and it can also be used along with color addition and subtraction. This is the method used to create the gradient in the text boxes in Final Fantasy III. And finally, any windowing effect that isn't just vertical bars uses HDMA to modify the left and right boundaries of the window while the image is rendered. Super Metroid has a few windowing effects, one for the eye shining its light beam, and another for the power bombs. And with that, the PPU-centric chapters of this series come to a close. The next video will be about controllers and gamepads, and how input is taken from the player's hands and fed into the software. As always, thank you for watching.